Okay, yesterday I went through the content or just the theory of work, energy, and power, but I think maybe I did it a bit too quickly. Okay, so I'm going to look at the individual concepts and I'm going to try to tie them together for you again. But I think it's going to make a lot more sense when we go through the homework that I gave you. Okay, so we started off by defining work, and we said work is equal to the magnitude of the force multiplied by the magnitude of the displacement. And I told you this theta value, that theta is the angle between whatever force you are interested in and the displacement. So I drew a little picture for you and I showed you in my rough work. When I do rough work, I include on my diagram the displacement so that I can clearly see the angle between the displacement and the different sources. So I recommend that you guys do this as well, but you do it for yourself on the question paper. You do it so that the marker does not see it. Okay, when we were done with that, I explained to you there are many ways in which you can calculate net work. You can calculate net work by saying the net force multiplied by the displacement multiplied by cos the angle between the net force, I think I said net work, the net force and the displacement. Okay, so once you are done calculating the net force, if the object is accelerating, it's speeding up, then you know the net force is in the same direction as the displacement. And for my diagram over here, what will the theta value be? 0. They are both pointing towards the right. They are parallel to each other. And based on that, for this diagram, the theta value is going to be 0. Okay. Then another way in which you can calculate the net work is to add up the different works. Now you'll see very often in your exam guidelines, so those marking guidelines, when you look at a marking guideline, you're going to see they often leave out in this calculation the work done by the normal force, for example. Sometimes they leave out Fg. Why do they leave that out? Or in which case would they leave that out? Yes. Okay. These forces, if you look at my diagram at the top, here is my normal force. There it is. And in this case, the normal force is making a 90-degree angle with the displacement. So if I am going to calculate the work done by the normal force, it's going to equal to the normal force, the magnitude of the normal force, multiplied by the displacement, cos theta. But in this case, what is the theta going to be? 90 degrees. They are perpendicular to each other. So the theta value is going to be 90. Now if you use any calculator and it's on the right setting and you plug in cos 90, the answer you're going to get is 0. So as a result, any force that is 90 degrees to the displacement is going to do 0 work. And that is why we just leave it out of the exam marking guidelines. If you look at any memo marking guidelines, if you see there's works that are missing, it's probably because the work done by those forces is 0. Okay, if you want to include it in your calculation, however, you will not be penalized. In fact, if it's going to help you to think, then include it. Okay? Then there was this where I told you guys we get 2 types of forces. We get conservative forces and non-conservative forces. So if we are looking at the net work is the sum of all of the works, right? And if we only get conservative and non-conservative forces, then the work done by the conservative forces plus the work done by the non-conservative forces is the net work. I told you guys I looked at a few past papers, and I could only identify in those past papers one type of conservative force. What is that force? Fg, the gravitational force. Okay, so you guys, if you're looking at the system and you would like to know what the work done by the conservative forces is or are, then you are looking at the work done by gravity. Okay. Non-conservative forces, those include all of your other forces, except these ones that I've mentioned there. But guys, an applied force, okay, so if I push on the box, that applied force is a non-conservative force. Friction force, you guys know that friction is a non-conservative force, but friction is not your only non-conservative force. The normal force, is normal force conservative or non-conservative? It's non-conservative. You almost never ever calculate the work done by the normal force, but the normal force is a non-conservative force. So everything else is going to be a non-conservative force because it is path dependent. It depends on the actual path that we have traveled in order for you to calculate the work. Okay, now from that, I said to you guys, if we are looking at mechanical energy is a type of energy. Right now, you guys can hear the sound of my voice. Those are sound waves, energy that is moving towards your ears. Sound is a form of energy, but it's not mechanical energy. We have light from the light bulbs. That is also energy, but it's not mechanical energy, it's light energy. It's electrical energy that has been converted into light. So we get all of these different types of energies, but if we speak about mechanical energy, then we are talking about the sum. Guys, what does the word sum mean? To add. Okay, we are talking about the sum of the gravitational potential energy and the kinetic energy of the object. So kinetic energy is a type of mechanical energy. Potential energy is a type of part of mechanical energy. And together they tell us the mechanical energy of the object. Basically, mechanical energy answers this question. Where is this thing in the gravitational field and how fast is it moving? That is what mechanical energy is about. And everything we are doing is actually about mechanical energy. Okay. So this formula here at the top, from your principle of conservation of mechanical energy, as well as these two at the bottom, based on the work energy theorem, they are all related to each other. And the biggest question I always get from my learners, from you guys as well, is, ma'am, I see the problem. I see I need to calculate something about work, but how do I know which formula to use? In most cases, grade 12s, you can probably use at least two in most cases. And that is why if you look at the memos, the marking guidelines for this section, you're going to see there are about 5 options for one question. Okay, it makes it very difficult to mark this, but there's about 5 options because there are multiple ways in which you can calculate this. So for this section, you need to be confident. You need to believe in yourself, you need to carry it through, and just hope that you're on the right track. But of course, if you know your theory, then you probably are on the right track. You're going to practice and practice and practice with this summary page in front of you until you get confident and you find that you're always getting it right. Okay? But if we look at this one right at the top, the principle of conservation of mechanical energy. A moment ago at the left-hand corner of the screen, on your page, I spoke about conservative forces. And you guys told me there's one conservative force that we deal with. What is that force? Gravitational force. So, when do we use the principle of conservation of mechanical energy? It's when the only forces that do work are conservative forces. If you have non-conservative forces, if you have a pushing force on the box, if you have friction acting on the box, if you have any non-conservative force, then grade 12s, you may not use this formula. This formula you're normally going to use when you have an object moving, for example, on a frictionless surface, with only Fg being the force pulling down on that object. Or for example, when we have an object in free fall, okay? So an object starts with there and falls down. And also yesterday I mentioned to you, sometimes you might have a pendulum. Okay, a ball attached to a string and it will be moving in space. Now just to quickly talk about this pendulum. If I tell you we have a pendulum and it's moving in space and I ask you to identify the forces. So here's the ceiling, there's a rope and there's a ball. And it's going to swing back and forth in the air. Assuming there's no air resistance. What forces are acting on this ball? Okay, number one, we have the gravitational force. So there's a downwards Fg. What else? A tension force. Okay. Now the tension force is not a conservative force. It's not. And yet I am telling you that you may use the principle of conservation of mechanical energy for a pendulum. The reason why we can use this principle here is simply because although there are two forces here, one that is non-conservative and one that is conservative, only one of these forces is doing work. So what is going to happen is this pendulum is going to move. It's going to have a trajectory something like that. If we draw a tangent over here, right, there's my tangent. Then for this little moment, the displacement is that way. Do you agree with me? Does everybody see that? For the moment that it moves, just at this point, it's going to move down like that. Okay. Now looking at this displacement and looking at the tension force, what is the angle between them? 90 degrees. The angle here is 90 degrees. And when a force acts at 90 degrees to the displacement, how much work does it do? Zero. So the reason why in this case we can use the principle of conservation of mechanical energy is because there is only one force doing work, and that force is a conservative force. It is the gravitational force. A few learners walked in. Does everybody have the notes? Is there anyone who needs notes? Okay, so we're all fine. Okay, it's the same notes as yesterday. If you were here yesterday, then you have the notes. Okay. Alright, so conservation of mechanical energy, when can I use it? When I only have conservative forces doing work on the object. Okay, so in other words, when the work done by the non-conservative forces is equal to zero. You're going to see that at the bottom of this graph. Are there any questions? Okay. Now let's say that you do have non-conservative forces acting on this object, whatever the object may be. In that case, you are limited. You can't use the principle of conservation of mechanical energy. You're going to have to use one of these two. So you're either going to have to use the work energy theorem or the work energy theorem in general. Both of them are on your formula sheet. Remember, your formula sheet is at the back of your theory booklet, so please familiarize yourselves with it. But if you look at these two, they are actually the same thing. Mathematically, we can prove that they work out to exactly the same thing. I'm not going to do the proof. If you're planning on studying BSc Physics next year, then your whole life is going to be about proofs. Okay, when you do BSc Physics, it's just about manipulating equations for the biggest part. Okay, but looking at these two formulae, they are basically the same, right? Or you can use this one to derive this formula. You need to know how to expand them. Just as I have over here, so I didn't do this on your page, and I asked you guys to fill it in yesterday. And this one over here, I have also expanded for you. Make sure you know how to expand them, because this version is not given to you on your formula sheet. Okay, but they do give you potential energy, and they do give you kinetic energy. So before your exam, you're going to look at your formula sheet, you're going to see what's not there, you're going to fill in what's not there, and you're going to remember it, please. If you know your formula sheet, you're going to find it a lot easier to navigate through your exam, and you're also not going to waste time. You guys spend a lot of time trying to find formula, and that's the last thing you should be wasting time on in an exam. Okay. Lastly over here, I spoke about power yesterday. I told you guys this is the one formula, that's the other. I'm not going to spend too much time on power, but I'm going to ask that you guys please cancel this out. It says here, when an object moves at a constant speed along a rough horizontal surface. The surface actually doesn't need to be rough. I'm not too sure why I said rough there, but you can take away the rough. It will work whether it's rough or frictionless. So that is the summary of the theory from yesterday. I'm now going to look at that homework you guys have to do. I'm hoping that in doing that work, you are able to at minimum see what you don't do. Okay, when you are studying, you're not trying to get everything right. That is not your aim. When you're studying, you're trying to make mistakes, to learn how to fix them, so that when you get into the exam, you can get it right. Okay, so if you are trying a past paper and you are just going through the paper, easy peasy, everything right, something is wrong. The paper is not difficult enough. Find a more challenging paper. If you are studying the CAP syllabus, go and try an IB paper to really test yourself. Okay, but don't settle and don't become content with your life. Okay, so I asked you guys to do question number 5, and I also asked you to do this content question number 4. I'm going to start off with the question number 4, and then I'll go back to question number 5. Okay, question number 5 is there so that you guys can see a different way of doing things, something you're unfamiliar with, and it also relates to what I taught you guys right at the beginning, those graphs, direct proportion, and so on. Okay, so in this question, question number 4 from your content paper, okay, they say we have a wooden box, and this wooden box slides down a rough 8-meter long inclined plane AB. Okay, the word rough, what does it imply? Friction. Okay, so nothing's there for nothing. We don't just use words to decorate the page. It's actually there to tell you we're going to have friction. Now you see the way this diagram is illustrated can be a little bit confusing because you see this box or the motion of the box, we're not going to analyze from this point. We are actually looking at it from this point when it starts to slide down to point B. Okay, so that means your free body diagram needs to look like this, the one I wrote in blue, and not like that, the one at the top that was there originally. Okay, so they've given us the length of the displacement to be 8 meters, and they go on and they say the initial velocity of the box at A is 2 meters per second. We have an initial velocity. We know the formulae that contain initial velocity is your principle of conservation of mechanical energy, your work energy theorem, and your work energy theorem in general. So we know somewhere in this problem we're probably going to be making use of that. But at this point, of those 3 formulae, there's one that I can delete. Which one do I know based on what I have read that I cannot use in this problem? There you go. Principle of conservation of mechanical energy. We cannot use the sum of, or just the mechanical energy at the top is equal to the mechanical energy at the bottom. We can't use this formula. By the way, this formula is not given to you on your formula sheet, so you need to know it. Okay, but you can't use this. The reason we cannot use this is because there is friction. And friction is a non-conservative force. It's not only gravity that's doing work here, we also have a non-conservative force doing work. So at least we can eliminate this formula, which leaves us with 2. Okay, we go on and they say here's the sketch. You can see in the sketch they've also given us the angle of the incline, that's important information. And they've given us the fact that the mass of this object is 2 kilograms. So don't get confused. The initial velocity is 2 meters per second, and the mass is 2 kilograms. Okay, they've given us quite a bit of information. Question number 4.1 says, define a conservative force, right? I'm not going to write it on the board, but we say it's a force for which the work done in moving an object between 2 points is independent of the path taken. Key words there, guys. If you did not say force for which the work done, if you just say force for which, or the force that is independent, then you're going to be serious. We need to see force for which the work done is independent of the path taken. Okay, and if you write that down correctly, you're going to get 2 marks. Where do we learn our definitions from? Exam guidelines. Again, if you don't know where to find them, come and speak to me. I will direct you to all of the exam guidelines. Okay, so you learn this off by heart from your exam guidelines. 15% of your paper is more or less definitions. Okay, number 4.2 says name the conservative force in the diagram. So before we even do that, let's just quickly see what forces are acting on this box. What do we have? Okay, we have a downwards gravitational force. I told you guys always straight down. Where does the split go? Straight down. Okay. Then what else we have? A normal force. This object is on a surface. Guys, please be very careful. When you have an object in free fall, so here we're talking about vertical projectile motion. Vertical projectile motion is when the only force acting on the object is Fg. And yet I still see some of you in your exams saying there's an upwards normal force. Be careful. A normal force is exerted by a surface on an object. So if something is just falling through space, there's no upwards normal force holding it up. Okay, so please be very careful. Objects in free fall do not have normal forces acting on it. When the bouncy ball hits the ground, the normal force will act on it. But while it's flying through the sky, no normal force. Okay, there's one other force we need to indicate. What is it? Friction. Okay, so we also have friction. So the question is, of these three forces, which one of the forces is the conservative force? Gravitational force. Now some of you would have written this down, Fg. I can't guarantee it, but there's a big chance they will give you 0. Why would they give you 0? They said here, name the conservative force. It's a mistake that you guys make most often in chemistry, in organic chemistry. We say to you guys, write down the formula of the compound. Or we say to you, write down the name of the compound, or something of that sort. And instead of writing down H2SO4, you say sulfuric acid. Or instead of writing down sulfuric acid, you write down H2SO4. And guys, they're going to give you 0. We give you 0. Because we are not only testing, if you know physics, we are testing to see if you are law of abiding, that word, citizen. Do you follow instructions? We said name. So if we say name, then we're going to say gravitational force. That's going to get us our mark. We have named it. What's another name for the gravitational force? Weight. Yes, weight. Your weight is a gravitational force, okay? If you say the force of gravity, that's fine, okay, but weight. Remember, when you get onto a scale, the scale doesn't give you your weight, it gives you your mass. I don't know why we use the term weight on a day-to-day basis, but weight is a force. Your mass, if you weigh 50 kilograms, that is your mass, not your weight. Okay, so gravitational force or weight, that is going to get you your y. And if you wrote this down, give yourself a 0 and tell yourself why, so that you never make that mistake again. Okay, the next one. Now, you see, over here, and this is how we normally, not all the time, structure our questions. Here we said define a conservative force. In the next question we said name it. You see, the definition leads you to the next answer. Now we say state the work energy theorem. Most of the time, grade 12, they say state a theorem, state a principle. Not all the time, but more often than not. It's because they're trying to say to you, you're probably going to need to use this and therefore you need to know it. Okay, so I'm not going to write this one down for 2 marks. You should have said, the net work done on an object by a net force is equal to the change in the object's kinetic energy. Or something of that sort, you just copy it down from your exam guidelines. Okay, are there any questions? Then we're in 4.4, and I'm going to try to spend a lot of time on this. So if you're really good at work, energy, and power, please forgive me. Okay, I guess you can only get better, but I'm going to spend a lot of time on this. They now say the velocity of the block at point B is 6.92 meters per second. So what are we going to do? We're going to go to our sketch, and over here we're going to say V final equals 6.92 meters per second. We fill that in. It's information that has been given to us. Then they say use energy principles only to calculate the frictional force that the block experiences as it moves from point A to point B. Now, if you have practiced a lot on this, you will know for this section, you can also use things like F net equals ma, and from this, you can go use an equation of motion to get the correct answer. Okay, I've seen it in many textbooks. I use the answer series textbook and they do it in the answer series. If you use this method to answer this question, and you got everything correct, you are going to get 0 out of 4. Okay. Why? Because grade 12 they say use energy principles. So if you do anything else other than obey the instructions, they're going to give you 0, and they are very, very strict with this. Okay, the places where we try to be lenient because we say, oh shame, poor grade 12. But when it comes to things like this, we're not going to be lenient. Okay, so what are we trying to find? We are trying to find the magnitude of the frictional force. That is our goal. Okay? Looking at this and remembering our energy principles, I'm going to have it space. Okay? What we know right now at this point is we know the object's mass is 2 kilograms. We know its initial velocity is 2 meters per second. We know its final velocity is given as 6,92. So we have initial and final velocities. Okay. We know we can't use the principle of conservation of mechanical energy, which leaves us with only 2 formulas. The one formula we have is work net is equal to change in EK, and the other one that we have is the work done by the non-conservative forces is equal to the change in kinetic energy plus the change in potential energy. You could use either of these formulae in order to answer this question. Okay, so there's a chance that the way I worked this out is not the way that you did, but if your answer is correct, you probably got 4 marks. Because again, there are just so many ways in which you can work this out. Okay, let's start off with network. Go back to our diagram. Okay. According to this diagram, we're going to draw a free body diagram. We have the normal force, friction, and Fg, and the object is moving down the incline. So a free body diagram for the situation is going to look something like this. Normal force, Fg, and over here, change in x. No, not change in x, friction. The object is moving down the incline. So since it's moving down the incline, in your rough work, you're going to go and fill in that the displacement is there. Already we know that one of these forces is not going to do work. Which force is it? The normal force. You see, the normal force is perpendicular to the displacement. So we know the work done by the normal force is equal to 0. Okay. So if I would like to calculate the net work, I need to add together all of the works. In this case, we're going to say the work done by friction plus the work done by the gravitational force is going to equal to the change in kinetic energy. Change always means final minus initial, so I'm going to say half mv final squared minus half mv initial squared. Okay. Are we happy? Alright. Now there are many ways in which you can calculate Fg. Right? I'm going to expand on this even further. If you want to calculate the work done by friction, you want to say the friction force multiplied by the displacement cos theta, where this theta belongs to that over there. Okay. For Fg, there are lots of different ways. Okay. So the first method I'm going to use is the one where we use the actual displacement. Okay. When you are done with that, I'm going to show you there are other things which you could have substituted into that place. So you're going to say plus Fg. To calculate Fg, we can just say mg, right? Change in x cos theta. Okay. is equal to, on the right hand side, half mv final squared minus half mv initial squared. Okay, I've expanded. Are there any questions so far? Okay, we are looking for the friction, so I'm going to leave this as F. The displacement going down the incline, what is the measurement? 8. So I'm going to plug in 8 in the place of x. If you look at this, here is my displacement. Okay? It's going down the incline. What is the angle between F and the displacement? 180 degrees. So in the place of the theta, which is the angle between the friction and the displacement, we're going to go and put in cos 180. And that is friction for now. If we look at Fg, the mass of the object is equal to 2. G is always 9,8. And if by any chance you forget this, any chance, it's on the data sheet in the formula sheet. So attached to your formula sheet, you're going to see this is there as well. By the way, in that data sheet, you're also going to find the radius of the Earth, the mass of the Earth, the charge on an electron. So we don't need to state it to you in a question. You need to know it's on that data sheet. Familiarize yourself with the data sheet, please. Okay, now I said for this specific problem, I'm going to use the actual displacement. The actual displacement is that this object is going down the incline. So in the place of x, I'm going to put in 8. Okay, and now we have a problem. We need to find out what theta is, where theta is the angle between the actual Fg and the displacement. Okay, so we are basically looking for this angle over there. That's what we're looking for. You can go all the way around, you're welcome to do so, but we're looking for this angle, the angle between the displacement and Fg. So now your ability to draw your free body diagrams, your ability to break forces up into components, that becomes important. And guys, that is grade 11 work. So you're often going to find that the reason why you're struggling with grade 12 work is because the foundation is not there. Okay, don't be scared to go backwards in order to build this part properly. Looking at this diagram, remember my FG is straight down. FG has components. It has an FG perpendicular and always down the slope. We're going to have FG parallel. Okay, we fine? Okay, remember FG parallel must always be down the slope. If it's not down the slope, then it will be slipping up an incline, and that doesn't happen. Okay, now looking at this, what is the value of the angle over here? It's going to equal to the angle of the incline. So we know over here we have a 30 degrees. Okay? I know that my displacement is there, and I am looking for the angle between Fg, which is over there, and the displacement. There's the angle I'm looking for. Okay. Between Fg perpendicular and the displacement, what is the angle? Let me ask again. Fg perpendicular over there and the displacement, what is the angle? 90. Between Fg perpendicular and the displacement, it's 90. So what I'm coming to, guys, is this whole angle. Let me draw it again. I think my drawing is horrible. Okay, so there's my Fg. Okay, I drew in the components of Fg. Fg perpendicular, this is the one I was asking about. And we said down the incline is Fg parallel. So my question was, between the displacement and Fg perpendicular, what is the angle? The angle is 90. And based on that, some of you said this angle is therefore 60 degrees. Because 90 minus 30 is 60. So if I am using the actual Fg, I need the angle between the displacement and the actual Fg we are working with. And based on that, when I come to this here formula, I'm now going to go and say the angle between Fg and the displacement is going to be 60 degrees. Okay. Now, guys, there are other ways in which you could have calculated this. Methods that some of you think are a lot easier. That's what becomes confusing. There are just 100 different ways of doing this. Right now, what I did was, I said, we can calculate the work done by Fg by saying Fg, change in x cos theta, where this angle is between Fg and that, and we got a 60 degrees. Okay. There are two other methods we can use. The next one is we can say the work done by Fg is equal to Fg multiplied by change in x cos theta, where this change in x is going to be the height through which the object moved. And some of you are more comfortable with this. So I explained to you guys yesterday, you're welcome to use the height for Fg because Fg is a conservative force. So let's go back to our sketch. If we want to do that instead, and it's really just about what you're more comfortable with. If we would like to do a calculation like that, let's try that again. So let's say, height, okay. If I want to use Fg, and I want to make use of the height, when this object moves down, okay, when it goes from there to there, it moves through a height. It starts there and it ends up on the ground. Okay, so what Fg is doing is essentially taking this object and its work is in moving it downwards. Okay. So what we can do is we can start off by calculating this height. Over here we have a right angle triangle, so I can complete it like that. We have a 30 degrees there and we know that this is 8. I am looking for the opposite side. This here is the hypotenuse. What type of trig ratio makes use of opposite and hypotenuse? Side. So what we can do is we can say to calculate this height, we can say sine 30 degrees, right, is going to be equal to the opposite side, the height, over the hypotenuse, which is 8. So to find the height, if we solve for the height, we're going to get 8 sine theta. Okay, where this theta is 30 degree angle. Lots of angles, and I think sometimes the angles confuse you guys as well. Okay, are there any questions about what I just did? So what we can now do is we can say in this formula, as the height for this problem, we're going to plug in our Fg. In the place of the height, so now I'm going to use red, I'm going to plug in 8 sine 30 degrees. Okay? And now this theta angle, this theta over there, is the angle between the displacement, which is the height, and Fg. So think about it, this object starts at the top of an incline and it moves down to the bottom. That is its displacement. I'm going to use a y because it is a vertical displacement. Fg, if we draw in Fg, Fg is also down. So what is the angle between Fg and the height through which it moves? 0. So in this case, our cos theta is going to be 0. At the top of here, to perform the same calculation, we said Fg, we used the 8, and we said cos 60 degrees, because here we are using the actual Fg with the actual displacement. In this case, we're using the actual Fg with the height as the displacement, and as a result of that, the angle change. Okay, so now we have 2 methods so far. Are there any questions? Okay, it's intense, challenging, but you guys can do this. Okay, there's one more method you can use. Okay, I hope I haven't lost you guys yet. The other and the last method is to say, to calculate the work done by Fg, we can say the work done by Fg is equal to the work that its parallel component does. So looking back at my sketch over here, okay, if we are looking at Fg again, we know that Fg is straight down. We know Fg can be broken up into its components. We have Fg perpendicular and Fg parallel. Now, if you look at the components of FG, only one of these components is parallel to the displacement. Which component of FG is parallel to the displacement? FG parallel. So what I can do is I can use the displacement with FG parallel, and that will also give me the work done by FG. Okay, the section is confusing because there's 100 different methods, and all of them are going to get you the correct answer if you use it correctly. Okay, so you're going to use change in x cos theta, where this theta value over here is the angle between the displacement and FG parallel. But that means we need to first calculate FG parallel. Okay, and when we calculate FG parallel, there's a theta involved. So going back to my sketch, we know this angle here is 30 degrees. To get FG parallel, what am I going to use? Cos or sine? Sine. It is oppositely angled, so to calculate FG parallel, we're going to use FG sine theta. This theta has nothing to do with work, energy, and power. This theta is this angle over there. Okay? So when you see this in your marking guidelines, they're going to expand it like this. They're going to say it's equal to FG. We said we're going to use sine theta, okay? The displacement change in x, cos theta. And you need to understand that this theta is about this. This theta over here is the angle between this and the displacement. There are different thetas. So when we calculate this, we're going to calculate FG. We're going to plug in sine 30 degrees. This is the angle of the incline. We're going to plug in the 8 and cos. The parallel component is in the same direction as the displacement, so it's going to be cos 0. And all three of these calculations are going to mathematically give you the same thing. Okay, you're going to practice until you get it right. Over and over and over again until you get it right. Okay, so coming back to the actual problem, our goal was to find the value of friction. I plugged in one version of calculating the work done by FG, and what is missing now is everything on the right hand side. So what am I going to do? I'm going to plug in half, the mass is 2. Make sure you use the correct final velocity. The final velocity is this 6,92, not the 2. So we plug in 6,92. My learners always then forget to square because you're nervous, your anxiety has kicked in, you're in a rush. Don't forget to square. Then we're going to minus half 2 multiplied by 2 squared, where this 2 is the initial velocity. Then you're just going to move everything around mathematically, and in the end, the final answer you should have obtained for the friction is 4,31 newtons. Okay, you got 4,31 newtons, you've done it correctly. There are other methods, and I'll show you another one just like this. If you use the principle of conservation of mechanical energy, then
and then you minus, you say, let's say EMA equals EMP.
so you want to use this. Did you end up getting exactly the same answer?
And then you minus the vertical volume.
Can you come show it to me afterwards? Okay. Because I'm a bit concerned because this over here, they might just mark it wrong simply because the principle doesn't hold. Alright? This principle won't hold again because of friction being present. Okay? But if it works out, I'll just have a look at yours. Okay? Alright. Would you guys like me to show you how to use this one? Yes, no, maybe. Yes. Okay. Right. Okay. Again, guys, there's normally going to be 2 formulas that you can use, okay? You have to be daring in this case. You need to just try and hope that you get some of it right. And if you struggle with work, energy, and power, what you must not do is get into your exam and leave it blank. Because there's a chance you might be able to sub one thing into it correctly and get at least 1 mark. So just to show you guys how we mark this, I think it's out of 4 marks. you're going to get 1 mark for your formula, 1 mark for substituting on the left-hand side, 1 mark for substituting on the right-hand side, and 1 mark for your final answer. But grade 12s, you're only going to get a mark for your final answer if you have the correct SI unit. Sometimes you guys are so overwhelmed by work energy power that you tell me friction is measured in joules. Be careful. Always go and check your SI unit. If you finish off your exam early, you don't just sit there or you don't sleep, you go back and go check that you did these small things. Squaring and the correct SI units, for example. Okay. Now I think it's important that you make use of this formula, that I show this to you guys, because some of you, maybe some chicks, maybe not you guys, have a bit of a misconception regarding WMC. A lot of the time, because in examples we use in class, the only non-conservative force in the situation is friction. You guys just go and plug in work done by friction over there. Okay? But there are cases where friction is not the only non-conservative force. This is not one of those cases. So over here, friction is the only non-conservative force doing work. We don't care about the normal force. But just to show you guys, if we had a box, just on the side, and maybe you can write this around that summary page. If you have a box and there's a force being applied that way, and I tell you there's friction as well, there'll be a normal force, Fg, so on. I give you initial velocities, final velocities, and so on, and you want to use this formula. Work NC in this case is not only equal to the work done by friction. It's equal to the work done by friction plus the work done by the applied force. This is actually the sum of all the non-conservative forces. And if you miss that, you're going to mess up and you're going to lose marks. I guess we should have written here a sigma symbol, that you knew it was the sum, but if you don't add all of them, you're not going to get your marks. Are there any questions about that? Okay, so work non-conservative is all of the non-conservative forces, including the normal force, but the normal force does zero work in almost all cases. Okay, actually in all cases. So coming back to this scenario, the only non-conservative force acting on this box and doing work is friction. So it narrows everything down for us. Okay? On the right-hand side, the biggest problem most learners have is going from the formula that is given to you to the expanded version. You must be very careful when you do this. Change always means final minus initial, but in the middle we have a plus sign over here, okay? So when we expand this and go and use your formula sheet for the formula for kinetic energy and potential energy, you're going to say half mv final squared minus half mv initial squared. This part is only that. We then write down the plus sign in between, and then we have change in potential energy. That is going to be mgh final minus mgh initial. If you want to go put brackets around it, you're welcome to do so, but it's final minus initial, final minus initial. Are we okay? Okay. Now if you use this, then you would need the final height and the initial height, which means you would be forced to use trigonometry. Height is always your vertical height, right? We're talking about gravitational potential energy, where this thing is in the gravitational field of the Earth. Okay, so you saw previously, we calculated the height by making use of our right-hand triangle. We said there's a 30 there, this side is 8, and we're looking for the height over there. It's a right angle triangle. So we said sine 30 degrees is equal to opposite the height over the hypotenuse. And based on this, the height over there, which I think solves to 4, is going to be equal to 8 sine 30 degrees. I multiply up by 8 to find the height. Okay. The object starts off at the top where the height is, in this case 4, if I'm not mistaken. and it goes down to the bottom, to the ground. What will the height be here at the bottom? 0. So the final height is 0. The initial height is going to be this. Okay, are we fine? If when you worked out the height you got decimals, so let's say it was 4.1, 2, 3, 4, 5, 7, 8, 10, whatever, right? You do not round that answer off. Remember I told you guys yesterday, you only round off right at the end of a problem. If you don't do so, you're going to be penalized if your answer is different from what's on the marking guidelines. So don't round off in between, please. At minimum, 5 decimal places if you really not feeling like writing everything down. Okay, so over here we have friction multiplied by the displacement, cos theta is going to equal to everything on that side. Our goal is to solve for friction, so we have F, displacement is 8, and this theta grade 12 is the angle between the friction and the displacement. The box is moving down the incline, its displacement is there, and friction is always in the opposite direction to the motion. So friction is going to be upwards. What is the angle between the displacement and friction? 180. So we go and put in cos 180 is equal to. Be careful, don't switch around your initials and finals. They told us when this object reaches point P, its velocity is going to be 6, something, 6.92. So it's going to be half times 2, the mass in kilograms, times 6.92. I think I have that correct, yes. Remember to square it. You don't square it, you're going to lose marks. Minus half to the initial velocity is 2 at the top, and don't forget to square it. Are we okay? Are there any questions so far? Don't forget the height. Guys, if you had an object moving on a horizontal surface and you decided to make use of this formula, then the height in the beginning is going to be 0 and the height at the end is going to be 0. So you would just plug the 0 and the 0 in there. You can use this formula on a horizontal plane or on a horizontal surface. It's just the heights are going to be exactly the same, therefore 0 in both cases. Okay, so here we plug in our plus sign. The mass is still 2. G over here, we're dealing with scalar quantities. Gravitational potential energy is a scalar quantity. We plug in 9.8. The height in the end is 0. It's on the ground. Minus 2, 9.8. The height in the beginning is going to be, I'm going to plug in the whole thing. It's going to be 8, you say sine, 8 sine 30. And then we have every single thing that we need in the formula. Let's zoom out a bit. Okay, everything that we need has been plugged into these equations, into this formula. Please write neatly when you are completing your exam, not just for the marker but for yourselves. When you write untidily, I don't know what the word is, when you write in an untidy manner, what happens is you sometimes confuse yourself. You can't even see what you're writing down and then you start to panic. Okay, so now all we have to do is solve for friction. You plug all of this into your calculator and then you divide by 8 cos 180. And in the end, the final answer is going to be exactly the same, 4.13 newtons. You're going to get 1 mark for your formula, 1 mark for subbing on the left, 1 mark for subbing on the right, 1 mark for your final answer, provided you write down your unit of measurements. Yes, it is. Thank you. That'll be one. Okay, anything else? Yes.
The formula that you substituted into, it has work done by friction on the second step. Does that mean the work done by the non-conservative forces is equal to the work done by friction?
Correct. Yes. And on that note, guys, if you identify that the only work done by non-conservative forces is the work done by friction, And then instead of writing this formula as it appears on your formula sheet onto your page, and you instead write down work done by friction equals change in EK plus change in EP. You write this down. There's a chance that you might lose your formula now. Okay, so start off with what is on your formula sheet, then plug in the work done by friction, which I expanded there. I should have written this down, but I was lazy. That's why I didn't write it down. Okay, but always start off with the formula from your formula sheet. Is that a question?
I just want to ask, what do you use mark that indicate direction?
If you don't indicate direction, where?
It's the frictional force.
So do you mean if you don't show the cos theta?
And
At the end. Okay, no. In this section, we normally ask for the magnitude, if I'm not mistaken. So we never actually require you to show direction. Let's see, where is it? Okay, it does say calculate the frictional force. They should have said calculate the magnitude of the frictional force. But in this case, if you just want to be safe, then you're going to say up the incline. Okay? And please note that this formula is not going to give you direction. Okay? Because this f that you just solved for is the magnitude of friction. Okay, I'm going to say it again. These formulae, the energy principle formulae, they're not going to give you direction. So you're going to have to go back, see where you drew in your arrows, and then write down the direction. But most of the time, they're going to ask for magnitude. Okay. On that note, when it comes to things like vertical projectile motion, Newton's laws, please remember to write down your direction. You leave that out and you're probably going to lose your marks. Okay. Are there any other questions? When I give you the marking guidelines, the memos at the end of the session, you're going to see there are more ways of doing this. Okay. All you need to do is make sure that each step that you do is correct. Also, please remember your exams are 150 marks. You have 180 minutes to complete a 150 mark exam, which is what you see, 150. So that means you have 1.2 minutes per mark. And if this question is out of 4 marks and you are spending 12 minutes, 15 minutes on it, you're wasting time. You're getting or you're pulling away time from something else. When you get into your exam, you time yourself. Just on the note of how you guys study. I know that according to brain, whatever, right, science, you can only concentrate for a limited period of time. It's a fact. Okay. But guys, what I see when I'm invigilating exams with the matrics, especially this current group of matrics, because you guys did a lot of homeschooling because of the pandemic and so on, my learners can't sit still during the exams. The legs are out and then they need to take a break and then they need to sleep and that sort of thing. And it's because we are no longer used to sitting for long periods of time focusing. So when you study, if you are planning, right, to be able to focus for, what did we say, 180 minutes, right? Am I right? 3 hours, right? You're planning on focusing on 3 hours to complete an exam. It does not make sense that you only study 15 minutes, take a half an hour break, study 15 minutes, take a half hour break. When I was in high school, I used to play soccer. The coach always used to say to us, you need to practice the way you're going to play on the day of the game. So he used to say to us, if you're being lazy during practice time, there's no way we're going to perform better on the day of the match. Okay, if your fitness is not good on the day that you're practicing, you're not going to be able to make up for it when you are, well, writing the test. Okay, so you guys must try to study under exam conditions. I'm not going to say much about earphones because I don't know. Okay, I can't do what you guys do. But when you are in an exam room, there's no music playing to calm your nerves. Okay, and then you become anxious because you don't know the exam condition. You don't know how to pose in silence while focusing on something. So when you are studying, try to put yourself under exam conditions, okay? Sit there and try to not move and to just study for 3 hours straight and then give yourself a break. You're writing a 2-hour exam, study for 2 hours and then give yourself a break. You are not only learning the content, you're learning how to write an exam. And you might know all of the content, but because you don't know how to write an exam, because you can't cope under exam conditions, it doesn't matter. And you don't prove yourself in the sense that you don't get full marks, no marks you deserve. Okay. Anyway, let's go back to this problem. Okay. The very, very last problem over here. And I just again want to point out to you, they said in question 4.3, yeah, they said state the work energy theorem in words, and look at 4.4, we use the work energy theorem. Alright? So the next question says the coefficient of friction for the last horizontal stretch. So now we are moving over here. It's important that you read and that you're able to comprehend what you're reading. They say when we move over here, there's going to be friction. And the coefficient of the friction, not the friction, but the coefficient, make sure that you read carefully, is going to be 0.35. Then they say, calculate the distance the block will travel before coming to a complete stop without using motion. Without using equations of motion implies make use again of energy principles. Okay, so over here, what do we know? We know that this system operates sort of like a series. Where the previous series ends off is where the next one starts. Okay, so the box came down the incline and it got to this point where its velocity is 6.92. Now we don't care about it moving down the incline. Now we care about this horizontal motion. So here's my question. At the start of this motion, what is the velocity going to be? 6.92. Where we ended off the previous series is where we're going to start the next one. Okay, so here's episode 2. The initial is going to be 6.92. Okay, they tell us the object is going to move a certain distance, and then it's going to come to a stop where V final is going to equal to 0. Okay, now I'm sure there are many different ways in which we can perform this calculation, many different techniques we can use. What we make sure of, however, is that we must not make use of equations of motion. Okay, so which means that we must probably use energy principles. This box is no longer on the incline. It is now over here. And I'm sorry my page is so messy. I hope that the colors and so on are not confusing you guys. But now the box is there at the bottom. So this previous diagram that I drew, see this free body diagram on the right hand side, it no longer holds. As soon as the situation changes, you draw a new free body diagram. And this rule applies with Newton's laws as well. There are many Newton's laws problems where they tell you there's a tension force and suddenly the rope breaks. Then you must draw a new free body diagram. Or they'll tell you there's an applied force and suddenly the applied force is no longer there. You must use a new free body diagram. So looking at this box, what forces are acting in it? Okay, I hear gravitational force. I hear normal force. What else? Frictional force. Those are the only forces acting on this object. Fn, Fg, and friction. Okay. The object is moving that way. Okay, that's where its displacement is. Now looking at this, the normal force and Fg are equal and opposite, and they are also not doing any work. So if I ask you, which force over here, or which forces should I have to get the net force, what are you going to say? Only friction. Friction in this case is equal to the net force. Okay, so what am I going to do over here? I'm basically going to say, let's use the work energy theorem because we have initial and final velocity, and let's say the net work is equal to change in Ek. Guys, can you still hear me properly? Okay. Net work, how do we find net work? We can add together the works, right? Or we can say the net force multiplied by the displacement cos theta. But in this case, you guys just told me the net force is the friction. So we are simply going to say friction change in x cos theta equals half mv final squared minus half mv initial squared. And again, don't forget your squares. Okay, trial and error until you get it right. The friction force, to calculate friction force, yes, we got friction previously, but it is not the same. Okay, we are going to have to calculate it from scratch. They gave us the coefficient of friction. We know friction can be calculated by saying the coefficient multiplied by the normal force. And in this case, the normal force is equal to Fg. It's one of few cases where Fn is equal to Fg. So I can calculate this by saying the coefficient multiplied by mg. That is going to be 0.35 multiplied by 2 multiplied by 9.8. Okay, I plug that in, 0.35. You're welcome to work it out first. But then just remember, you must not round off and you must show your work in some way. Okay, so over here, 2 times 9.8. That is the friction that I've written down. We are looking for the displacement. That's what we're looking for. Cos theta. What is the angle between the friction and the displacement going to be? 180. Yes, they are equal. Opposite in direction. So it's 180. Then we plug in the final velocity is 0. They say it comes to a stop. Minus half. The mass is going to be 2. Initial velocity, we said, is what happened at the end of the previous series, 6.92. Okay, so we put in 6.92 squared, and all that we now need to do is solve for this displacement. Okay, and when you solve, you should get an answer equal to, we have 6.98 meters. This is probably not the only method you can use. You could, for example, use work done by the non-conservative forces, and then in the place of the height, you're going to have the same height, which makes this equal to 0. And this basically becomes the same as that equation. Okay, so you can use that formula as well. Alright, that is some of work initial power. I don't know, okay, in terms of time, we don't have a lot of time left. We have about an hour left. So I think instead of working through this one, I'm just going to point out some of the areas where you guys go wrong. Okay, well, work through some of the problems. This is also work energy and power problem, but for this problem they gave you a graph, which is different from what you used to. Okay, they said, how did you guys find this problem? Was it okay? Was it challenging? Where are we? In other words, do I work through the whole thing or only some of it? Some of it, okay. Alright, so they say a box is pushed from rest. In the beginning, this box has a velocity of 0. With a constant applied force equal to 30 meters. It moves over a horizontal surface with 3 different regions. Each region is 5 meters long and exerts different frictional forces on the box as it moves through. So here is our box. You can see here is the force being applied. And of course, in the opposite direction, the motion is going to be a friction force, which is going to change as it goes from 0 to 5, 5 to 10, 10 to 15. It's going to change. Let's say the graph below shows the kinetic energy of the object as a function of distance. Now just a note on this. When they give you the name of a graph, provided they've done so correctly, okay, provided it's correct, then we always say dependent variable versus independent variable. The dependent variable here is kinetic energy, the independent variable is distance. And as you can see, my stick falls onto the x-axis, the stone stays standing tall, and there's the dependent variable for this investigation. Okay, then they go on and they say from the starting point, as object experiences a constant applied force, the first region is from 0 to 5, second 5 to 10, and third 10 to 15. So looking at this graph, you can see that there are 3 lines with different gradients. This is region number 1. And immediately, based on the information that has been given to us, I'm going to go and I'm going to say, you see this point? If I were to draw a line straight down, I'm going to get a number on the x-axis. And what is that number going to be? 5, yes. They said the first region is from 0 to 5. So grade 12, it means this line ends at 5. Does that make sense? Okay. The next region, the one that I'm drawing in green, it ends at a different point. And if I were to draw a line from this point down, what number should I get? 10, because it ends at 10. And then lastly, we have this one. And where should this one end? 15. They told us the third region ends at 15. So those are the data points on the x-axis. And I go and fill that in because I'm trying to make my life easier for as we get to the other problems. Okay. They said state the work energy theorem. We've done so before, so I'm going to skip it. And I'm going to go to 5.2. A very unique problem because I haven't seen in other past papers them asking me to prove something. They say use the work energy theorem, at least they've given you a hint, to show that the gradient of the slope represents the net force. Okay, this is actually a proof. So, if we look at the work energy theorem, we know that the work energy theorem says that the net work is going to be equal to the change in kinetic energy. Okay, that's the first thing we remember. Now guys, in physical science, when we speak of a gradient, we mean exactly the same thing as we do in mathematics. How do you calculate a gradient in math? Change in what? Change in y over change in x. In other words, change in whatever is on the y-axis over change in whatever is on the x-axis. That is what we are saying. Okay. So if we are to calculate a gradient for this graph, then we are going to say the gradient is equal to change in y over change in x. The y values are kinetic energy values. So we're going to say change in kinetic energy over change in x values is distance. So in other words, position, right? And that's going to be change in x. That is what the gradient is. Now looking at this formula over there, we need to now ask ourselves, is there a relationship between this formula and the gradient which we just calculated? So look here. If I take the work energy theorem, work net is equal to change in K. I can expand the left hand side and I can say the net work is also the net force, change in x, cos theta. Let's assume the theta value is 0, which means cos theta is just 1. Okay? And that's going to equal to change in ek. I can then solve, or I can get this on one side by dividing both sides by change in x. And I'm going to end up with F net is equal to change in Ek over change in x. In doing so, I have just proven that the gradient, which is change in Ek over change in x, is equal to F net, change in Ek over change in x. In physics, gradients don't mean nothing. Gradients are normally physical quantities that we can calculate the gradient for to obtain. So in this case, what we are saying, grade 12, is if I say to you calculate the gradient of this yellow part, when you get that number is the net force that this box is going to experience as it moves from there to there. If I say to calculate the gradient of the blue line, That blue line gradient is going to be the net force from there to there. The gradient has an actual meaning. It's a physical quantity which you can obtain by manipulating the formula. And if you show anything of this sort, you're going to end up getting 2 marks. Are there any questions? This is very, very important when you get to electricity and the photoelectric effect. There your ability to manipulate your straight line becomes very important. Okay, just quickly, if we look at the first part of the motion, let's say that the rest of the graph was not there. If I were to ask you what is the relationship between distance and kinetic energy, what are you going to say? Are they directly proportional? How do you know that? Number one, straight line through the origin, straight line and it's through the origin. Okay, only if the line cuts through the origin and is a straight increasing line is it direct proportion. So if in a test I ask you, why is whatever graph direct proportion, you must say straight line through the origin. If you don't say through the origin, you're going to lose marks. Okay, are there any questions? So when we get to the next one, they say, calculate the net force experienced by the object in the third region. All that they are saying is, calculate the gradient of this blue line. That is what they say, because we've now established that the gradient is the net force. Okay, but what you guys must please do is, take the time to read the values off of the graph. Don't be too quick about it and make sure you get the correct numbers. Because previously, so in the exam that the Gauteng learners wrote this past term, I found that a lot of learners did not take the correct values off of the graph. So you actually need to go and count. We know that this point over here has the x value 10. We don't know what the y value is. We're going to have to read it off. If we look at this point, it has the x value 15. We don't know what the y value is. We're going to have to read it off. So now you're going to have to count. If every 2 blocks is 40, then it means every 1 block is 20. 60, 80, 100, 140, okay, that's what we know so far. If it takes 5 small blocks to get to 20, then it means each little small line represents 4 units. And based on that, this point over there is over here at 88. Okay, and that you can read off of this accurately. So in other words, if you did not use 88, you're not going to get your marks. Okay, over here we can clearly see this point goes all the way there to 180. And all that you're now going to do is use these points to calculate your gradient, and that gradient is going to be your net force. Yes. For now, I'm going to say no. So given that this graph is very clear, and the points can be easily, what is called, read off of it, in this case we will penalize you. So if you look at the memo which I'm going to give to you guys, you're going to see they don't give a range. They don't say from this to that. But if it's unclear and you need to estimate, then we'll give you a range. But for this one, there wasn't a range there. Okay. Any other questions, guys? Okay. The rest of this over here, I guess I will not go through unless you guys have one of the problems that you really want me to go through. Are there any questions that you want me desperately to solve? 5.6. Okay. So 5.6 is related to 5.5. Okay. This one over here, as long as you understand the previous ones, you'll be able to say, I think in this case, net force equals sum of forces or something like that. Okay. Alright, they say, which region offers the largest frictional force? Okay. All that we can see from these different regions is the gradients of the graphs. And what did we say the gradients represent? The net force. Okay. We proved here on the side that the gradient is the net force. Okay. So looking at these gradients, we can see the gradients are changing. We first have a steep gradient, less steep gradient, and a steeper gradient. The gradients are different for the different regions, which means that the net force is changing. Okay. Now looking at our box over here, if I am to draw a free body diagram for this box of only the horizontal forces, then I will say we have the applied force and we have a backwards frictional force. Okay. You guys know your grade 11 content, you know Newton's laws. If we would like to calculate the net force for this box, what are we going to do? We're going to add the forces, right? We choose one direction as positive and we then say the force minus friction. That is how we're going to get this. Okay. If you are one of those learners that put plus signs everywhere and only when you substitute you put in the negative, that's fine. But in the end, you're going to subtract the friction value from the applied forces value. So looking at this equation, when will the net force be the smallest? Remember, this is constant. It's a constant 30 newtons. To make this 30 newtons small, what do I need to do over there? Make the friction big. If the friction is very big, it's difficult to move this box, and therefore the net force is going to be small. A large friction is going to produce a small net force. Okay, so what did the first question say? It said, which region offers the largest friction? Largest friction means smallest net force. And we said the net force is represented by the gradients. Where is the gradient the smallest? Region 1, 2 or 3? 2. The gradient is the smallest there. This over here is the hill that we're all going to manage to run up. These other ones, they are a lot steeper. Okay, so the gradient here is the smallest, meaning the net force here is the smallest. So to answer question number 5.5, the correct answer is the C. To answer question 5.6, although it's only out of 2 marks, we are explaining. So I want you guys to think about what I taught you yesterday. In the section explanations, in your physics paper, explanation is about 35% of your paper. And how are you going to answer this? You're going to think control, independent variable, dependent variable, and the relationship between the two. So looking at all of these regions and the information given to us, what is constant in every single region? The applied force. Guys, they said here at the top, a constant applied force of 13 newtons acts on the box. It means no matter where we are pushing at 13 newtons. So number 1, we are going to mention the applied force is constant. And you guys will write this out in full, but I'm being lazy. Is constant in all regions. Okay. Number 2, we know what is changing in the different regions is friction. And what does friction change? It changes the net force. When the friction is small, the net force is high. When the friction is high, the net force is low. So now we are going to say over here, since this over here is the same in all regions, we know, I'm going to state this the right way, when the friction is large or largest, the net force is going to be the smallest. Okay, in this specific problem, this is my independent variable. I'm looking at what friction does to net force. Okay. The second region, I'm now tying it to the graph. The second region has the smallest gradient and therefore the smallest net force. And that is why the correct answer is the second. Okay. If the question is out of 2 marks, I'm looking for 2 points. Don't write one statement and feel satisfied about it. I want you guys to be controlled, independent, dependent. And even if you don't state it in that order, at least it will give you a bit of a method to think about the problem. Okay, now in this problem, we're not getting a mark for the first statement. I stated it just to help us think. You're going to get a mark for this one and that one. And if we're looking for formulas, the formula I used was F length equals F minus friction. That is what I used to answer this question. Are there any questions for us? For therefore, you can use the symbol therefore. Okay, but when it comes to other things like applied force, friction, net force, my suggestion is write out the full word. And if you're uncomfortable with your spelling or something of that sort, in brackets next to it, put the symbol. Okay? For direct proportion, don't do this. Don't do that. Write down they are directly proportional. Inversely proportional, don't use symbols. Explain yourself in words, please. And you can use symbols on the side, just for in case you spelled something wrong, but you must explain in words. Therefore, though, you can use the dots. Okay? Are there any other questions? Okay. It's a challenging section, and unfortunately, I can't give you guys a procedure. Because again, I know your question. Your question is, but ma'am, how do I choose the correct formula? And unfortunately, it's not something where I can say, step 1, do this, step 2, do that, and so on. All I can tell you guys is that most of the time, you'll be able to use 2 or 3 formulae. And you must always remember that if there are any non-conservative forces, you eliminate the principle of conservation of mechanical energy. Okay, but there are going to be lots and lots of options. So if you have time, if you finish your exam like 30 minutes before the end, go try the other options on the question paper to see if you get to the same answer, because then you know it's correct. Okay. We're going to take a bit of a break from my talking, and I'm going to ask you guys to do a bit of work. Okay. The next thing I want to speak about is vertical projectile motion, and I also want to speak about momentum and swing paths. We don't have a lot of time, but let's see how far we get. Okay. So I did not write down where these are from. Let's just see. From your 15th paper, I want you guys to do multiple choice question number 1.3. So this is the 15th paper. Then the next one is from the Northwest paper. Yes. Okay, not Northwest, Western paper. You're going to do Western paper question 1.4. And the very last one, I guess, is from the Northwest paper. Okay, so you're doing 1.3, 1.4, and 1.3. Okay, for this section, I'm not going to talk about everything. I'm just going to highlight the important things. Number 1, there's a difference in your exam guidelines between the definition of a projectile and free fall. A slight difference. A projectile is an object, I don't use my pen, it's an object that you give an initial velocity. And guys, it doesn't only mean we are throwing it up. You can also throw something down. And in that case, it would be a projectile. So in the definition of the projectile, you're going to see an object which has been given an initial velocity, and then after that, everything flows like free fall, and then moves under the influence of gravitational force. What my learners always leave out is only. You must say only gravitational force. Because right now, this bottle has the gravitational force acting on it. It is there. But is this a projectile? No. Because it also has the normal force acting on it. And as a result, the bottle is not a projectile. So you have to use the word only. But specifically, projectile is something that has been thrown into the air, thrown down. If we're talking about hot air balloons, that is a projectile. Because you know, if you have an object that falls off the edge of a hot air balloon. If this hot air balloon was moving at 2 meters per second up, then this object, when it is dropped, will start off by moving up for a little bit and then it will go down. So it has an initial velocity equal to 2 meters per second as well. Therefore, it's a projectile. That hot air balloon is doing what my hand would be doing if I threw something up. Okay, not throw up, but throw it into the air. Okay, then we have free fall. Free fall is the second part of this definition, and it says motion. They said when we were marking the previous paper that you guys wrote, for 10 learners, that the word motion must be there. So it's motion during which the only force acting on the object is gravitational force. So if you said an object which moves under the influence of gravitational force only, you get 4 marks for free fall. But for projectile, you must say initial velocity. Big problem in this section is that a lot of learners forget this. In this section, we are dealing with vectors. You leave out direction, then every single one of your substitutions is going to be incorrect. The first thing you're going to do is check, do they tell you which direction to take as positive? Because if they tell you, you must stick to that. But if you say, okay, I'm going to choose down as positive, then from question 3.1 to 3.2 to 3.6, you must take down as positive. You must be consistent. I had a learner who was changing. With each question he would change. And as a result, going from one question to the next, it was wrong. Okay, so you must be consistent with your direction. What in your equation is a vector? Basically everything. All quantities are vectors except the type. That means everything has a negative or positive attached to it. You guys know in physics, negative and positive means direction. So if we are choosing down as positive, then into our equation, the A is going to be positive 9.8. If I'm throwing it up into the air at 2 meters per second, the initial velocity is going to be negative. If down is positive, up is negative. And you must substitute those negatives in. So my advice is if you're someone who gets anxious, you're someone who gets nervous when you start to write an exam, when you get into your paper, you're going to go to question number 2, 3, 4. Most of the time that's what it is. But in other words, the Newton questions, you're going to go to vertical projectile motion, and you're going to go to momentum and impulse. You're going to find those questions. And you're going to write down at the top of each of those pages direction so that you don't forget it. It's so easy to forget direction. Your answers must have direction, and when you substitute in, you must have direction. It's a very easy way to get everything wrong by leaving it out. Are we happy, guys? Okay? Often in between questions in this section, like in the Gauteng paper that was written last term, in the middle they say, what is the acceleration of the object? And what so many of my learners did was they performed a calculation. And they got A equals some weird number. In vertical projectile motion, the acceleration is equal to G, which is 9.8 meters per second squared. Don't forget the square. It's always that. Unless the object falls onto the ground and has a net force in another direction acting on it, acceleration is always 9.8 meters per second squared. The way they catch you guys out is they make it out of 2 marks, which makes you think you need to do a lot. Now I need to do a calculation. There must be something more to it. But it's actually just 1 mark for 9.8 meters per second squared and 1 mark for down. Alright, please be very, very, very careful. If my object is thrown into the sky, reaches its maximum height and then falls back down. At the maximum height, what is the acceleration of this object going to be? It's going to be 9.8 meters per second squared down. Even though the velocity at the max height is 0, the acceleration is still 9.8 meters per second squared down. Please don't forget that. Just because the object for a moment stops to change direction does not mean that its acceleration is zero. We normally draw the trajectory, that word, like this. But in this section, guys, we are actually dealing with one-dimensional motion, which is actually just an object goes straight up and comes straight down along the same path. That is actually what we're dealing with. And you see, if something goes straight up, the only way it can come straight down is by stopping and then coming straight down. Okay. Another problem I see. When the object comes back down and meets the ground, is its final velocity going to be zero? No. If you think this final velocity is zero, then I want us to perform an experiment. You're going to lie on the ground over here with your head close to the table. I'm going to stand on the table with the brick, okay, and I'm going to drop it. When that brick hits your head, is it going to hit your head with a velocity of zero? No, that's why it's going to hurt. Because when this thing hits the ground, its velocity is not zero. It will become zero because the ground exerts a force upwards and brings it to a stop. So you guys, because you're so used to seeing you throw something and it stops, you think the final velocity is zero, but it's not. It becomes zero after interacting with the ground. But when we look at our projectile, when that projectile comes down and hits the ground, it's going to hit it with a maximum velocity. And that is why you will not stand beneath the table and allow me to drop the brick, because you know it's going to hit your head very, very hard, because it will have a velocity. It won't just stop. Oops, there's a head, I'm going to stop. It's going to hit you. Okay? Be careful. Now, all the time I've been told the biggest problem in this section is the graphs. Okay? Unfortunately, with graphs it takes a lot of practice, and I don't know if I might be if I'm way off, but I find that a lot of learners who find geometry and even your graphs, so your parabolas, hyperboles, and math, tend to find this section easy. And then there's the rest who struggle with it. So you're just going to have to practice until you get it right. And what I want you to remember at minimum is, if we're looking at a position time graph, then the gradient gives us velocity. Okay, so looking at this over here, a tangent, you guys all know what a tangent is, right? If we draw a tangent here, it has a gradient. If we draw a tangent there, it has a gradient. If we draw a tangent to the graph at the top, it also has a gradient. Is the gradient of the tangent increasing or decreasing? Is it becoming more steep or less steep? Less steep. See, it starts off very steep. The red one is steep. If you have to climb up that, it would be difficult. And then it becomes less steep, less steep, less steep, until it becomes zero. This gradient tells us what is happening with the velocity. Look at my velocity. It starts off big. Okay? And what is my velocity doing? Just like the gradient is decreasing, my velocity goes from a number like 5 to 4 to 3 to 2 to 1 and 0. Now the velocity is 0. Where is it 0? At the maximum height. So you see this point over here on this graph, it corresponds with that point on the velocity graph. When you have a turning point on a position time graph, it is actually a turning point, or where the object will stop, change around. It's at the maximum height. This turning point is the max height. But where you have an x-intercept on a velocity time graph, that x-intercept is going to be the max height. Because at the maximum height, the velocity is 0. The object stops, then it can turn around and come back down. Okay. Then what happens is, we see after this point, our gradient goes from being 0, and slowly, the gradient becomes steeper and steeper and steeper. It becomes more and more easy for you to slip down the incline. The gradient is increasing. And it continues to increase and increase and increase. What we then see is our velocity time graph goes from 0 and it increases in the negative direction. Your brains tell you that this is a decrease. It's not a decrease. If I have numbers on the side, numbers like 1, 5, and so on, what is happening is, although they are negative numbers, we go from 0 to -1 to -5. 1 is a higher velocity than 0. 5 is a higher velocity than 0. This section over here that you're seeing at the bottom is the object speeding up in the negative direction. That is what is happening over there. Okay, and you guys need to create links between these two graphs. So if I highlight, we know that the little point in the middle that I have in yellow, that is the maximum height. There it is. The initial point is here. There's the initial point on the velocity time graph. Okay. Over here, this point where it passes through the origin and comes back to its starting point, that is this point over here. And the end position for this one over here is over there. Okay. When we look at an acceleration time graph for this section, it's always a straight line, and it's going to be at a value on the y-axis of -9,8 or +9,8. We say that when you look at a velocity time graph, the gradient gives you acceleration. We have a constant gradient, so if you are to calculate the value of this gradient, you're going to get 9,8. -9,8, because the graph leans that way. In mathematics, that's a negative gradient. Okay, if your graph was leaning that way, you'd have a straight line over there, because then you have a positive gradient. Sometimes we give you a velocity time graph and we say, from the velocity time graph, determine displacement or distance traveled. To calculate the displacement or the distance, we consider the sum of the area under the graph. So I'm talking about this region. We'll use half base times height, it's a triangle, and we'll use this region between the x-axis and the actual graph. Calculate those areas, half base times height, and we will add them together, the positive values to get distance, or we will add them together, this one being negative, to get displacement. Okay. Are there any questions? Yes.
So you only consider the signs when you calculate displacement?
Correct. Okay. You are only going to consider the sign. So let's say I tell you, calculate the displacement. Yeah? For this triangle, if this is 10 and that's 6 on the time, then we know that this length is 4. Because 10 minus 6 is 4. You all with me? Okay. Don't use 10, please. It's this part, it's not that part. So 10 minus 6 gives us 4. Then let's say this point over here is -10. That's the height of the triangle. And when you're calculating displacement, you are going to use the negative because displacement takes direction into consideration. When you're calculating distance, you're just going to use half 4 times +10. You're not going to use the direction at all. Does that answer your question? Okay. Are there any other questions? Yes.
Throw something on the wall.
Yes.
And you throw it up.
Yes.
If you add that velocity to the velocity of the
Will you add that velocity to?
velocity of the so you let's say you throw it
Oh.
up 8 meters per second, and the 8 meters per second.
Yes, in that case. I haven't seen an example like that, but yes, you have.
And I did it by around when you throw it down.
Yes, you have to subtract. Okay, that's now an advanced question. But I explain to you guys what he's asking. He's saying, let's say you have a hot air balloon, and this hot air balloon is moving up at 2 meters per second. And then you are standing in this hot air balloon, and you take your cell phone, because you're done with your cell phone, you want to study for your exams, okay? And what you're going to do is you're going to throw it. But while you're in your hot air balloon, you're going to take this and you're going to throw it up. Let's say you throw it up, you personally apply a force that throws it up at 30 meters per second. Then, for a person who is on the ground observing this, they are going to see the cell phone move up at 5 meters per second. It's going to be the hot air balloon plus that. Here we're talking about relative motion, but I haven't seen a question like this before. If there is one, I doubt we'll use it for a long question. It'll be somewhere in the multiple choice section. Unless you're an IB student, they can get a bit tricky. Okay. Are there any other questions? Right, all about relative motion. I'll deal with it in a moment. Let's say, for example, guys, you are in a car. Just to explain this, just so you guys understand the physics behind it. Let's say that you are in a car and there's someone, you are traveling at 100 kilometers per hour and the car in front of you is traveling at 120 kilometers per hour. To you in this car, it's not going to look like this one is moving at 120. It's going to look as though if this car is traveling at 20 kilometers per hour. It's about relative motion. Where am I and what do I see in my frame of reference? Okay. For the person standing on the side of the road, though, they are going to say, this one's moving at 120, this one's moving at 100. For a child seated in this car who isn't paying attention to the surroundings, if you ask this child how fast is this car traveling, they may even say this car is traveling in that direction away from them at 20 kilometers per hour. Have you ever sat in a bus or just a car and there's a big bus next to you and suddenly the car next to you takes off? It feels as though the car is moving back, but actually the car is just moving forward. It's all about relative, your frame of reference. What am I observing and what do I see from that frame of reference? So that is what this is about, but I don't want you guys to panic about it. So you had a question?
So I just ask, how do you reference the reference addition and subtraction vectors?
Say again?
Is this subtraction and addition of vectors?
This over here that I'm speaking about, yes. It's just
If
that.
you had a scalar quantity to that, that is just multiply.
What do you mean add a scalar quantity?
Like I've seen a question where they'll add a scalar quantity and then ask how that is vector.
I'm going to need an example.
I'll
Okay, alright, because normally see we would never add scalar quantities to vectors, but if for example I said to you we have force equals mass times acceleration, and I go and I add on to the mass, then of course it will affect the force. Okay.
You just multiply the vector by the scalar quantity added.
Are you maybe talking about a case where they say to you, at the moment the force, the net force being applied is F, and they say to you the mass is double.
No, that's if they physically added a scalar quantity that affects
I'm not too sure. Okay. Alright, come to speak to me about it afterwards. Okay. Guys, after the session, you guys have an hour break. If any of you have questions, you can come and ask me. Okay. Are there any other questions? We okay? Alright, so let's go on to question 1.3 and will be answered. How much time do we have? We only have 5 minutes left. Oh shit. Okay. They say a ball is dropped from a certain height above the ground and bounces a few times. As it hits the ground, the velocity time drop below. Describe the motion of the ball from the time it is dropped. In relation to the velocity time graph for the bouncing ball shown above, which statement we know is correct? Okay. They say some direction is taken as the positive direction, and then they speak about the highest point. Alright. If we look at this graph, what is happening is the ball is being dropped. Drop means it starts off at a velocity of 0. When you drop a ball, in which direction will it go? Down. So as we go down, we see the graph goes into the negative direction. That means down was taken as negative, and of course up was taken as positive. Number 1. Number 2, they speak about which point shows the maximum height. Maximum height, if you go back to this graph, you'll remember where we have an x-intercept. That corresponds with maximum height. So in this case, the maximum height is point D. Okay, not point C, D. What is happening over here is the ball goes down, that's this part. Then it interacts with the ground and it's going to bounce up at the maximum height, that's this part. It reaches its maximum height over there, and then this over here is where it comes down again and interacts with the ground. Okay, so D is the maximum height. This here is the corresponding position time block. So the correct answer is down is taken as negative, and the maximum height, the highest point is point D. So D is correct. You guys agree with me? Okay, the next one, the velocity versus time graph below. It is in movement of an object that is initially projected vertically upwards. Okay, it's thrown into the sky. And as it goes up, we see it slows down. That's what's happening here. Slows down, reaches its maximum height, turns around and accelerates downwards. That is what we're seeing. They say the maximum height of the object reaches after the projection point is given back. Okay, the maximum height is going to be this point. Ooh, but it depends. I would say this over here is the maximum height above the projection point. They don't say maximum height from the ground. It's I'm standing on the table, I throw something up, it comes down and it passes. But we want to know the height from this point. Okay, so that is this point over here, or this area. Remember, to get height or distance from a velocity time graph, we make use of area. So this is a triangle. We say half. The base is t. The height is v. Half et. The correct answer is A. Okay, if you would like to know the maximum height above the ground, the 0 point, then you're going to calculate this area. Yes.
You also use a equation of motion.
Yes, yes, you can. You get the same answer. Yes, you are done too. Okay, the last problem, and then time is up. They say over here, a rocket is launched vertically upwards by a missile. Velocity time graph below depicts the motion of the rocket. Indicate the point on the graph where the rocket has maximum potential energy. It will have maximum potential energy at its highest point. What is the velocity at the highest point? 0. So that means 3. And the correct answer is C. Okay. Guys, there's a lot more that I would like to go through with you. Lots of other things I would have wanted to point out. For example, just very quickly, if you are looking at elastic versus inelastic collisions, remember, linear momentum is conserved in inelastic and elastic collisions. So don't think that just because it's inelastic, you can't use conservation of linear momentum. Also, if we ask you to prove that a collision is elastic, do not start off by saying sum of EK V4 is equal to sum of EK5. If you start by doing this, we automatically subtract 1 mark, right? Because you are assuming something. You must first calculate the total kinetic energy before, then on a separate calculation, calculate the total kinetic energy after, and then come to a conclusion. So you're going to see on the summary page, I've included that, so it's over here. There's a lot of mistakes that happen here, but you do this, then separately you do that, and then you come to a conclusion. Okay, guys, if you have any other problems, if you are, for example, I don't know what the word is, if you're doing homeschooling and you are struggling or whatever, you're going to see in my notes, I've included contact details, okay? You can make use of that. I won't necessarily reply, I'm very busy, but make use of that. If you find that